Hi everyone. Today we're going to continue our investigations on life sciences. Before we get started, I want to start off with a little demonstration. What I have here is a mason jar, and I have regular water that I'm going to just pour into the mason jar. And I have a plain note card that I'm going to place right on top. And what I'm going to do is flip it upside down and take my hand away. Well, we know that there's air in the room. Air pressure is holding the note card up and keeping all the water inside the jar. But what do you think happens when I take the note card away? Well, I have a big bowl here to catch all the water that may spill. But let's try it. I'm going to slowly take it away. A little bit of water spilled, but the rest is still in here. How did that happen? How is the water still inside the jar? What if I give it a little tilt? Poured all of it out. Not a trick. How did the water stay in there? Let's do some more experiments and see if we can figure out what is going on. Before we can understand the last experiment, let's try something else. I have a vase filled with water, and I have a paper clip. And I want to see if my paper clip will sink or will it float if I place it right on top of the water. It sunk. Let's try it again. Let's see if I place it a little bit slower. If I can get it to float. Nope, sunk again. Pause this video and you try to see if you can get a paper clip to float in a body of water. Small container or glass will do. Well, did you get it? Were you able to get the paper clip to float? I'm going to show you a trick that will teach us how we can get a paper clip to float. First, I'm going to take a small piece of tissue paper and place it right on top of the water. Place my paper clip right on top of there. And very, very carefully, I'm going to try to slide the tissue off and see if I'm able to keep the paper clip afloat. Oh yes, I did it. Look at that. The paper clip is now floating where it wasn't able to float before. How is this happening? How is the paper clip staying on top and how is it floating? Well, let's see if it's permanently stuck or if I can get it to sink again. Oh, there it goes. Went back down. It is no longer staying afloat. How was I able to get this paper clip to float when I had the tiny piece of tissue under it, but not before? The answer to that is surface tension. As I put the tissue paper right on top of the water, well, water starts to tighten up and becomes cohesive. All the tiny little water molecules stick together and they actually form stronger bonds. And that allows the paper clip to float on top of the water. Now, why is this important and what does that have to do with life science? Well, today we're going to investigate living organisms, animals that are able to walk on water, water walkers and water striders. More than 1,200 animal species have evolved the ability to walk on water. Tiny creatures such as insects and spiders can do it, and larger ones such as some reptiles, birds, and even mammals have also developed this talent. The tiniest animals are gliders. Insects, such as water striders and spiders, such as fisher spiders, can glide across the surface of water. These critters are small enough that their weight can be supported almost entirely by surface tension, the relatively weak forces that hold water molecules together. For these animals, gliding across the water is actually similar to how you might bounce on a trampoline. When tiny water-walking insects or spiders press against their water, their feet bend or deform the surface, but don't break through it. The surface then bounces back, propelling the tiny water walker forward. Surface tension makes this type of locomotion possible. Water molecules stick to other water molecules around them in all directions, and molecules at the surface of a lake have no water molecules above them, so they tend to stick more strongly to their neighbors, forming a firm, like layer across the surface. Water repellent or water-fearing feet are required too. These animals have a microscopic layer of dense hairs on their legs that can be coated with water-repellent wax, or the hairs can trap a cushion of air around their legs. Without this adaptation, the water would soak right through their feet like they were sinking through the trampoline. Pretty cool. That's amazing, right? Who knew animals could walk on water? Well, we're going to create a model of different types of animals and see if we can get those to also walk on water or glide on water. Let's do an experiment. Let me show you what you'll need. For the slab, you will need to provide a large container of water, tape, 4 pennies. From your enrichment bag, you will need 6 paper clips and 4 sponges. We will be making 3 different models. We will be using 2 paper clips per model. What you will first do is open up the paper clips. And to make the body, you will overlap them, making an X. And using a small piece of tape, you will connect the 2 X's together. This is what my first will look like. I'm going to do this 2 more times. Now I have the beginning of my 3 different organisms, my 3 different models. The first one is going to stay as is. It's not going to get anything added on. The second one is going to get pennies attached to each of its 4 legs, like so. I'm going to use a little bit of tape. And the third one is going to get sponges connected to each of the 4 legs. Going to go ahead and start connecting those. Here is the model of my second organism. Again, body with pennies. And now for my last organism, I'm just going to poke the sponge through the paper clip, like so. Now that I have my 3 different models, what I want you to do is make a prediction as to whether it will float or whether it will sink. Go ahead, pause this video, make your predictions, and then we're going to test it. I'm going to start with my first water walker and see if it will float or sink. I'm going to drop it in and immediately sunk to the bottom. That was no surprise to me though. My paper clips also sunk before they had the napkin in front of them. Number 1 did not float. Going to now try water walker number 2. Now I have something on the legs. I have these pennies. Will these pennies be able to provide the surface tension they need to float? I'm going to drop them in slowly. And nope, this sunk again. Water walker number 2 did not float. Let's drop in our third water walker and see what happens here. Well, look at that. This one is floating. We have our first float. Let's review what we did today. We were investigating to see if we were able to make a model of water walkers or water striders. We used different materials. We used paper clips as the body and different materials for their feet. The first one, which was just paper clips, nothing on its feet, we dropped it in, did not float. The second one also had a paperclip body, but pennies on its feet and did not float. But this last one had sponges on its feet, and this one was able to float. Now, water walkers, their feet are not made out of sponges, and this was just a model just to demonstrate how an insect or even a bigger animal would be able to float on water. Has to do with both surface tension and hydrophobic feet. Now, remember this jar and how I was able to pour the water in and flipped it upside down and it didn't fall? Do you know how that happened? Surface tension again, that's right. There was a little trick that I didn't show you. I'll show you now. I did pour water in here and I did place a note card, flipped it upside down, but I didn't show you what was at the very top. There's a little bit of netting, and that netting is what creates the surface tension. Puts pressure on the water starts to tighten up and hold on to one another and not let go. Same thing that happens when water walkers walk on water. Their feet are able to create surface tension on the water. It's so cool. Go ahead, try this experiment. Make sure to record your hypothesis and your results. Good luck and have fun.